enabling the digital economy.
Right, thanks everybody for coming to this Lunch and Learn session. I'm Professor Uwe Aickelin from the University of Melbourne, and I'll probably try and answer some of the questions at least that you've been asking. It's a big topic, AI, and what I'm trying to achieve with this talk is give you a bit of a flavor of what it is, what it isn't, maybe bust some myths. I'll try. I'll do my best. I'll also maybe surprise you with one or two things. Just by way of introduction, I'm from the University of Melbourne. If you're not familiar with this, it's a large comprehensive university in Melbourne. We have about 50,000 students. We are typically ranked #1 in Australia, and in computer science, we have about 100 members of staff. A lot of them work in AI. I'm the head of school there as well. And we're also rated quite highly in the world, we're number 14 at the moment. So I think we have a good bank of knowledge in Melbourne about this topic. So what I want to talk about is AI, and I've chosen this slide to begin with. This is going to be probably one of the surprises. There's a reason evolution will feature in the talk. This is actually, so I've been doing this for 20 years. I did my own PhD about 20 years ago, and I got into AI actually based on something like this. And I'm still fascinated by AI because of evolution, and I want to talk a little bit about that, because I think that's, to me, is more AI than some other things. So broadly, what are we going to talk about? We have a little bit from me, what's AI, what's not AI. And I want to give you a little bit of a technical knowledge. I mean, it's obviously, we only have 40 minutes, so I can't go into a lot of detail, but I want you to go away not just with a bit of philosophy. I want you to have a little bit of technical understanding. So I'm going to go through 3 algorithms, a little bit. And then we're going to finish the talk with sort of more wider and bigger issues around law and data and ethics and how do all these things come together with AI. Okay, so what is AI and what isn't AI? I mean, the first thing usually when I talk with people about AI is they say, you do robots, or maybe they think science fiction. And I usually say, no, not robots. So yes, in robots, there is usually some AI, but AI itself is nothing to do with robotics. AI is usually software, it's usually algorithms, it's something on the soft side. And really, robotics is not the biggest application at all. It's a very minor application. The biggest application of AI is what I would say decision support broadly. So it's something about making better decisions, reducing costs, maybe optimizing resources. That actually is probably broadly the biggest application. And when we talk about this, then it's usually about trying to get better answers or sometimes also get new understanding. And I mean, some typical examples would be to predict some pricing or just to segment our customers or maybe do fraud detection. That's quite popular. So it's not robotics. Now, another topic that often comes up when we talk about AI, and this is usually over a beer, is, this is artificial life. We're going to create a new something, Frankenstein cell or something. This picture, by the way, is one of my own research projects where we actually created some artificial dendritic cells. So we do sometimes work like this. But usually, AI is nothing to do with artificial life. So artificial life, something to do with reproduction. You know, we want to produce new life. That's what life is about. Intelligence is not to do with reproduction. Intelligence is about making decisions. Intelligence is about maybe looking at data. Now, the best way I can explain this to you is like this. Not all life is intelligent, right? Some life is pretty stupid. So clearly, life and intelligence is not the same thing. So AI is not artificial life. And creating AI will not create artificial life. AI is an algorithm that makes decisions. Okay? It's not related to life. Now, perhaps the biggest confusion, and this has come up yesterday, for example. I went to a panel, and afterwards I had a discussion with quite a few people. The biggest confusion, I think, these days is actually this: AI and automation. So a lot of people confuse the two things, and let's spend a couple of minutes on trying to tease out what's the difference between the two, because I think this is a good message that you should understand. So in businesses, in hospitals, everywhere, we're trying to do things faster, better, quicker. We're automating things. And these days, we use a lot of software for this. We also use hardware for this. But usually it's software. And what do we mean by automation? Well, automation is doing the same job, but faster. Let the machine do the job. Let the computer do the job. that kind of thing. Monotonous things in particular. Filling in forms. Let's let the computer fill in the form. It's 1,000 forms. Let the computer collate the forms. That kind of stuff. So it's usually about the collection data, the collation of data, and it's about being fast, being efficient, being accurate. But the key word I was going to say is about being obedient. You want the computer to do exactly what you want it to do. No surprises, please. And it's getting faster and faster and faster. And a lot of people confuse this with AI. They say, oh yeah, we have intelligent business systems now. They're not intelligent, they're just faster. Okay? Now, what's AI for me? And this brings me then back to my own studies and how I got into this whole topic and why evolution is so interesting to look at this. Well, for me, AI is something about thinking, right? How we think. So we want to simulate that. And it's usually software. Let's start there. I mean, AI is not hardware, it's software. And it's something about learning and creativity. In fact, creativity is perhaps the key word. And maybe that's missing a little bit in some of the AI world that we see, and we'll come back to that later. But even if it's about understanding of data, it's not about being obedient. It's about something new. You want to be surprised. You want the computer to come up with something, oh, I haven't thought of this. This is new. Now, that for me is AI. Okay? So it's not about being fast. It's not about being automated. It's about creation, creativity, something new. So now that we sort of covered that a little bit, I want to come back to my evolution slide, and I've got a few bad jokes here for you that amuse me. So I got into the whole thing of computing and artificial intelligence as a student because I came across this kind of thing, evolution. And I hadn't really thought about this much before. I mean, obviously biology in school, but then, in and out. And I came back to this 20 years ago, and I had a teacher who told me, oh, we can do this on a computer. And I'm like, what do you mean? So I started learning about evolution, and why would we want to do evolution on a computer, and what does that mean? And turns out that actually is artificial intelligence. So a few more little jokes for you. What do we mean by evolution? Well, obviously, we're talking a lot about phones. But let's come to the kind of picture that I first came across when I studied AI. It was actually something very similar to this picture here. So the challenge for you is you have to hide a fish in water. How would you do it? And then we're going to talk a little bit about how AI would do that. So I don't know how you would do it. Maybe I would paint the fish blue or something. I don't know. That kind of thing. Or put it behind a stone. Well, but how does nature hide a fish in water? Can you see the fish in this picture? Is it getting a bit clearer? You see it? So I have one more. It becomes a bit more obvious. It's this. It's actually a kind of seahorse called the leafy sea dragon. And it's fascinating how evolution has evolved this creature to be able to hide in water. I mean, it's doing a pretty good job. It's definitely in there somewhere. If you have a close look, it's actually that thing in the middle. Now, that to me is fascinating. And this is a creative solution. And this is not a solution that we would have thought of. And that's what I want in AI. I want AI to be like this, because I think that's where the value comes, and that's where we can do really new things. So how do we do that? Well, I'll just show you something jumping ahead. I mean, this has been used. It's called evolutionary computation. And it's been used already for 10, 20 years in many areas. For example, it's been used to design an engineering, design a nozzle. This is for aircraft refueling. And, the engineers started with something like this. It's pretty efficient. And, I don't know thermodynamics and all this, but this does pretty well. And then they applied this kind of algorithm to it. And have a look what solution they come up with. That was the solution. And that solution performed much better than the original. And again, no human designer would have thought of this kind of, it looks weird and complicated, and that is AI for me, coming up with something like this, okay? So how does this work? So I said I wanted to give you a little bit of technical knowledge, so we'll have a couple of slides just on, okay, how does this kind of algorithm actually work? Well, I already told you, it's kind of inspired by nature. It's inspired by evolution, by Darwin, survival of the fittest. And somehow we want to generate solutions, we want to optimize a problem, and there has to be some sort of generational process. And commonly, these kind of algorithms might be called genetic algorithms or evolutionary algorithms, or there's some sub-flavors to this, whether they're based on ants or immune systems or particles, and you might have come across any of these kind of words. Myself, I studied actually the immune systems quite a bit because I thought it's a particularly interesting mechanism, how we evolve and how we manage to survive. So how would an algorithm like this work? Well, you basically would first of all have to come up with writing down the solution, a bit like a genetic string. So you end up, traditionally you end up with zeros and ones, but these days you can write them down also in letters and alphabets and whatever, but you basically end up with strings. And the idea is that originally you start off with random solutions, maybe 1,000 random solutions, and then you iterate and iterate and iterate, and every time you iterate, you cut solutions in half, say, and you put two together, or maybe you mutate just little bits in the solution. And what you then do is you have 1,000 old ones, the parents, and you have 1,000 new ones, the children, so to speak, and you put them together and you say, well, let's keep the 1,000 best of these. And if you keep doing that, they slowly, slowly, slowly get better and better and better. And you can also bias this process more by giving the better solution a higher chance of mating, and there's sort of other tricks you can play. But eventually, you, over time, evolve solutions like that. And in the end, you stop whenever you had enough, maybe when the solution is quite good. So this has been applied to many problems. It's been applied in finance. So for example, typical prediction problem, I don't know, let's say we want to predict, here's an accounting, we want to predict, is this company going to go bankrupt next year or not? Or how long would it take? Or what's the health of this? And through this kind of string model, you can basically find out what's the variables we need to look at, how much weight should you put on these variables. And, similar to my nozzle, you have to imagine now the nozzle is all my variables. Some of them are going to be more important, some of them are going to be less important. And we might think of the top solution as being quite good, but the computer surprisingly comes up with really interesting combinations that we not thought of. So this is great, and I really love this approach. And for me, this really is AI, and we're going to come on to some other things which I think are a little bit less AI, but maybe more popular. It's, of course, not perfect. If you do this kind of algorithm, then the tricky bit is usually the first bit, which is writing down the solution. It's not always so obvious how to write it down, actually. I mean, if it's like 10 variables, then OK, sure, we just write down 10 variables. But what if the solution is a text, or the solution is some, I don't know, law or instruction or something? So it's not always obvious how to write it down. That's probably the hardest part. And then also, of course, at the heart of this, at the heart of evolution, is optimization. So we need to have some sort of idea of what we're actually optimizing. And again, sometimes that isn't obvious. It's a bit less difficult than the first step, but we need to think a bit about this. And of course, the final thing, this is not mathematics. This is not statistics. There's no proof that this is going to work. So there's pretty good evidence this will work, and there's pretty good evidence you end up with some good solutions. But it's very hard to guarantee exactly how good a thing is you end up with. OK, so now we've talked about what I think is AI. Let's talk about two very common approaches that I'm sure at this conference and in other places you will have come across that. And that's what most people would say AI is, which I think is OK. It also belongs somewhere to AI. But for me, these are less interesting, and I'll tell you why. So neural networks is perhaps the most popular one. Deep learning is the buzzword at the moment. That they've done a really good job rebranding themselves. This is the community. And what's the difference between deep learning and neural networks? There isn't a difference. Neural network used to be small, then they made them bigger and bigger and bigger, and then it became deep. And learning sounds better than network, I guess. So what's a neural network? Well, originally, this has been inspired by what's happening in our brain. We have some sort of processing in our brain where data comes in, we learn some rules, and we act on it. I look at the clouds, it's going to rain, I'll take an umbrella. It's that kind of thing. So in might go the weather and the temperature and what the cloud looks like, and out comes the decision, take an umbrella or not. That's a sort of application. So neural networks, very, very popular. It's probably the most popular approach these days. It's something called, this belongs in the broad category of supervised learning. Supervised learning meaning that we actually have some solutions for which we know whether they're good or bad, and we can learn based on these examples. And it's supervised because basically it's a reinforcement learner. So data goes in, output comes out, and we say, yes, that was the right thing, tick, we reward the algorithm, or we say, no, wrong, change something. And that's why it's called supervised, because we supervise what the algorithm is doing. And like I say, they're called neural networks because usually, they're called deep learning these days because usually pretty big. And they come in slightly different flavors, whether they're forwards and backwards, or whether they maybe even got some other special features. I'll show you a couple of pictures in a minute. And I've come across a report by McKinsey which says this is the technique is fantastic, and there's trillions of savings in this. So the most simple is the feed-forward network. That's kind of where it all started. Basically, you just have some inputs and maybe a single output even. Like I say, temperature goes in, sunshine goes in, weather goes in, and I just want to know umbrella, yes, no. And in the middle is a little function that computes temperature times clouds or whatever. And this is what we have to learn, of course, because we don't know what's this function. So I have some examples which I know the answer. I keep feeding them through. And it's a bit like the monkeys on the typewriter. If we let them type long enough, eventually the monkeys will produce the novel, right? That's exactly what happens here. Eventually, this algorithm will learn the weights because you just make it do that because it's supervised. So that's the most simple design. Nowadays, most networks aren't that simple anymore because there's some drawbacks if they're just like this. So we have more usually now recurrent networks, which basically means the information doesn't just flow one way, but the information can also flow back. And you get fairly complex structures like this. And with this kind of network, for example, you can then solve more difficult problems like speech recognition. And then even more than that, you might even have networks which are more complicated in the sense that the design is quite detailed. So you might have 5 layers, but a second layer is this big, the third layer is exactly this big, there's backwards connection between here and there. And anyway, so you end up with something called convolutional networks. This is usually when you have quite a good understanding of the problem. And actually, I used something like this for the finance application myself, where we had to do credit scoring. To put it simply. And we had customer segmentation already available, so we used customer segmentation as deciding how many layers and how many nodes in each layer. So we can combine these two things. So why do I not like neural networks? Oh, sorry. This is what I mentioned to you about McKinsey. I can give you the full details of this report later if you're interested, if you want to read up about it. But this is basically McKinsey saying this particular technology for different industries, what would be the impact? And you can see if some industries would be more impacted, I guess it's because there's more data there and more processing and more that can be automated still. And just as another example, what we could do with this kind of thing, apart from, like I said, customer segmentation is something we've done, credit scoring is something we've done, but you can use this for very wide applications. For example, predicting the maintenance of machines or coming up with other rules for hospitalization of patients or whatever. So I don't like this technique for the following reasons. And I actually, these days, don't encourage my students to use this anymore. First of all, it needs a lot of labeled data. It's a supervised method, so we need to have labels. We need to have examples. And I think this is getting increasingly difficult because our data sets are getting larger and larger, which is great on the one hand, but also bad on the other hand because we don't have the labels anymore. So I don't really think it's realistic to expect that in the future we're going to have all this fantastic labeled data. So that's one problem. Second problem is, well, the algorithm works. I mean, it will definitely learn what you want it to learn, but that's also the flaw because it usually overfits. And yes, I mean, there's many techniques then we're trying to prevent the overfitting. But I think ultimately this is the flaw of this technique and that we can't overcome it. So what that means is when the world changes, it just doesn't work anymore, or not so well anymore. So you might get more false negatives, for example, because the rules for yesterday are just not the rules from tomorrow. So this is part of the problem. But perhaps the main reason why I don't like this technique is the last one. I mean, look at this kind of setup. And this is not a difficult one. This is an easy one. So you construct this network, and you have all the weights and everything else in there. And the input goes in and the output comes out. But nobody understands what's going on. Even if the answer is right, I mean, surely the question is why? And we can't answer. Even the experts, professor of computer science, I look at this, I don't understand. And again, yes, there is some work going on trying to explain this, but I think fundamentally this is not going to be able to be explainable. It is a black box. And with what's happening in the law, what's happening around legislation and maybe legal cases coming up, I think black boxes are not going to be very acceptable in the future. So for these 3 reasons, I'm not sure this is a technology that I like very much. But it works, and it has its use, right? Let's come on to the third example I want to explain to you. I chose clustering as a representative technique from something called unsupervised learning. This is something I like better. So unsupervised learning is the opposite of supervised learning. It means we don't have to have labels, we don't have to have examples. We can just use the raw data. I mean raw as in maybe we have to make it look a bit good first, but it's pretty raw. And the idea of this kind of approach isn't so much finding out with the optimal answer. It's more a little bit about insights, a bit like a simulation. What's going on? So, the typical example, marketing, we have all our customers, and we kind of know there's 4 groups of them, the more affluent ones, and maybe the ones with families, and that kind of thing. And we want to segment our sales data somehow, and this is a typical example. How do we do this? And so I do like this better, because we don't need to have the labels, and I think this is something that scales much better with bigger data sizes. And I often use techniques like this. So just as one representative example of a simple clustering method, and one you may have heard in one of the other talks called k-means, the idea is that you take your data, we say, okay, we want to cluster it in k numbers of clusters, 4 clusters, and then we just assign the points to each cluster, and we always put them in the nearest cluster, basically. And we try to make sure the clusters don't overlap, and we try to make sure each point is close to a center, and then we recalculate where's the center, basically. So it's a simple optimization problem. This runs very fast. So typically, how would this algorithm work? Basically, take all the data in random order, assign each point to one of the clusters, and then as we assign a new point, basically the center of gravity of this cluster will change a little bit, and we'll just make the new center where the center of the points is. And we're trying to do this in such a way that the 4 clusters, if it's 4, they're as far away from each other as possible, but each point itself is as close to one of the centers as possible. That's why it's an optimization thing. So this works pretty well, and it's a great little algorithm, and there's many flavors again of this. Another way we can do clustering, so for k-means, I should say, one problem is we need to know how many clusters. If we don't know how many clusters, we can't do this. But how many clusters are there? Well, we could start with something like this, something called a hierarchical approach. It looks very pretty, like sort of a tree-shaped dendrogram. And we basically just sort the data by similarity. And we sort the data by similarity, and then we start from bottom up. We say the 2 most similar things, they belong together. And then the 3 most similar things, they belong together. And then, of course, I can keep doing that. And I might end up with structures that look a bit like this. So that's nice, because I don't have to say how many clusters there are. But maybe it doesn't give you a lot of insight. I mean, we're looking at these pictures. We might be able to say, oh, yeah, it looks like there is 4 clusters, or maybe it's 5, or, that kind of thing. And then, of course, these days, there is a lot of other varieties of clustering. Something I tend to use a lot these days is something called fuzzy clustering. It's a bit like the k-means, only we're not so strict. Things can be half in and half out. There can be 3/4 in one cluster and 1/4 in another cluster. And that makes a lot of sense to real-world data, because usually things aren't black and white. And this is a sort of a really neat approach of having clusters, having a cake and eat it, having clusters, but also have a little bit of flexibility around the edges, because that's really what it's like. So this is something which is a nice approach. Now, what's the problem with clustering? I do like it. How many clusters? That's a problem. If we don't know, then we can't use this approach, or we have to play around. I mean, in practice, what we do is we don't know the number of clusters, so we try with 2, 3, 4, 5, 6, 7, 8, 9, 10, some for example. I mean, just look at what the solutions look like, and we can also calculate different measures about the solutions. And they'll usually tell me how many clusters there are. A bit more fundamentally of difficulty is how to measure similarity. So all these approaches rely on having a similarity measure. And it can be easy if the data is numerical. We might calculate the statistic, or we might just calculate the distance, the geometric distance, or whatever, Hamming distance perhaps. But sometimes, especially when the data is not numerical, it's not obvious what's similar. So, let's say the data is colors, or the data is taste or opinions. But anyway, I mean, this is something we have to deal with. And then the last thing, a bit similar to the evolutionary algorithm, because these are heuristics now. They're not supervised. So we might end up with an answer, and it looks nice, but it's hard to tell how good it really is. I mean, yes, we can calculate some validity measures. How tight is it? How close is it? What's the shape of it? But they're all a bit indirect, and they don't really tell you, yes, that's a fantastic solution. So, having told you a little bit about three approaches to AI, I just want to sort of close this talk now with a little bit of sort of the bigger picture and what am I up to these days, what I think is a hot topic maybe as well. I mean, let's start with this first. Before I was in Melbourne, I was actually in China for 2 years, which was fascinating, looking at AI there. But before I was in China, I was in Europe. I was based in the UK. So I was quite familiar with European laws and legislations, and I guess Europe is leading a little bit on this. And I'm sure you've come across this new regulation about GDPR. And it does include something about AI in a way. So it's not really written about AI. It's written about data and data collection and so on. But of course, it does talk about data processing. And as we now know, a lot of data processing is done with AI these days. So it does touch on this. And perhaps the most interesting aspects of this law is that it seems to include a right of explanation, let's call it that. This hasn't been legally tested, so we don't know exactly yet what that means. And this will probably take 5-10 years to fully come out. But it does definitely strengthen the hand of the consumer. It does strengthen the hand of the legislator. And it points to me towards black boxes being less and less acceptable because we just can't justify anymore. This customer did not get a loan. Why? Well, computer says no. It's not going to be acceptable. Black box, not acceptable, I think. Sure, experts will be used, but I don't know. Perhaps my own prediction where a lot of this is going going to be some AI regulation in the future. I think we're going to get some sort of AI ISO 9000, some sort of international standard. I think that's where this is eventually going to go. But we're obviously away from that now. But for me, it means models should be simple, algorithms should be explainable. If it gets too complicated, there's going to be problems in the future, I think. So, explainable algorithms, and this is a bit of a buzzword in the research community at the moment. What does it actually mean? I mean, explainable to whom? Is that to school children or to legal experts, or is it to professors at a university? So, we need to understand that. And there's some sort of simplistic idea also that, if something is explainable, that means it must be fair. Well, no, these are very different things, right? I mean, I can write something which is really easy to explain, but it's completely biased. So they're not necessarily the same thing, so we also need to think about this. And this is some very interesting discussion around, well, policing was a good example. Data mining applied to policing, and then, it seems to be biased. Yeah, but that's because the data is biased, right? So what exactly do we want here? What's a fair algorithm? What's an explainable algorithm? The debates have not been fully had about this, and what the law will eventually decide, we don't know. But again, like I say, to me, all it means is keep it simple. Then we're in a good position later on. So what am I up to these days, and what sort of I think is a hot topic? Before we come to you to ask me questions, I want to tell you a bit about this. So I'm very interested in dealing with really difficult problems. I think that's where we want to use AI. Back to the idea of creativity. I think machine learning is very good techniques, and we can use clustering and deep learning, and they work very well. But it's a bit like statistics. It's a very powerful statistics, right? And it works very well. I want to go back to AI in the sense that it actually do something creative, do something different, do something surprising. And I think this is very well applied, not to the easy, or relatively easy problems, but more to the really difficult problems. And that's usually when people come in, because we are really difficult to deal with. And the sort of examples I work a lot with is where we deal with human experts, because that's all we have. We don't have a better answer. The gold standard is the human expert, whether that's a doctor in a hospital or a legal person or a finance expert. And all we can do is at the moment, we can say, okay, expert, have a look at this. What do you think? Is this patient ill or not ill? Or should we treat this medicine or that medicine? And the trouble with this is that, well, experts don't really agree with each other. No. But they don't even agree with themselves half the time. But that's the reality. This uncertainty is the reality. And how can we now use AI to support this kind of decision-making process? So I'm thinking, well, this is obviously, evolution has worked very well here. In evolution, we don't have a single person making decisions. We have teams, so we probably need teams of AIs, something like this. That could be interesting. And what we really want to achieve is something that's robust, right? I don't want something that works today and it doesn't work tomorrow and I have to fix it again and again. So we need to think a bit about this sort of robustness in this. And a team should be more robust because they can help each other. So that's what I'm working on these days, looking at what experts do, trying to do an AI a bit like this, helping the experts make better decisions, in the full knowledge that there is uncertainty and things are not really that straightforward and people disagree and things change. So with that, I've come to the end of my talk. And it's now your turn to ask me questions.